So we would like to discuss the different problems we face on matrix operations and different parallel machines. Some machines you will find that are suitable for matrix operations, some of them are not suitable at all. So it's based on the environment you have to decide the type of parallel machines is suitable for your matrix operation or something like that. You have to decide accordingly. Now, but if I ask that matrix of what are the different types of matrix operations generally we are encountering? One is multiplication and inverse. This is a very difficult problem. So first one is that simplest one is the transpose of a matrix. So one is the transpose of a matrix. Second one is the multiplication. And third one is not exactly inverse, it's actually inverse. Yes. Solution of linear equations. Right? This is actually, if you think the solution of linear equations, actually you are looking for inverse. Generally, inverse is used only for the simultaneous solution of linear equations, and we don't, in reality, we don't use the inverse thing. We use it different ways. We'll discuss this thing later on. First, the problem transpose. Transpose is not, even though it is a very simple operation that AI has to it, interactions with AGI. But it is a very difficult problem to solve. Say for I equals to 1 to n, for j is equals to and p is equals to aij, aij is equals to agi, and then agi. Right? This is the, and now these two parameters are important. Actually, these are, in general, we make several mistakes in the beginning, but it should be I plus 1 to n or 1 to I minus 1. Right? Yes or no? Right? So this is the transpose of this. Now, if I tell that you write a parallel algorithm for on shared memory model, how many processors on shared memory model? Suppose you have n processors, and this is the matrix of size n cross n, and then first processor is for this one, first row? No. Tell me. By now you should have some idea. You have told n processors.
For J2.
Huh?
For the J2.
First processor is first row. Huh? Second processor is second row, and ith processor in the ith row, and nth processor in. Right? So first processor's task is to interchange this with this. Right? Second processor task is to interchange. Is it the thing you are looking for? I don't know. Is it okay? Yes. Huh? No. Tell.
Processor will remain idle for
Only one job he will be doing. Right. But this is one way. And in that process, your complexity becomes order n, because first processor will be doing interchange of n minus 1 operation. Some condition here if you put, so otherwise it is order n time, right? So worst case, that you have to take the time needed by the first processor. And you will be putting order n time. Now suppose, so cost becomes order n square. Cost becomes order 1. So because order n processor and order n time, cost becomes order n square. And it is matching with this algorithm. Yes? There is no problem in that. Now suppose I use n square processor, right? Do you need n square processor? Do you need n square processor? Because if I have n square processors, these processors are idle. Basically, they will not be doing any job. So basically, you need n into n minus 1 divided by 2, this many processors basically, or of that order, minus n may be there, of that many processors for upper triangular matrix. And each processor is changing with this one, which takes only 1 unit of time. Agree? So, order n square processor, order 1 time, so cost is order n square, which is also cost optimal. Now, suppose I have mesh connected computer, 2-dimensional mesh. Now, how are you going to do it? You have a 2-dimensional mesh. So suppose you have this data 1, 2, 3, 4, 5, 6 up to 16, and you want to make the transpose. So this 1, 5, 9, 30 should go there, and 1, 2, 3, 4 should come here. Agree? Now that means that you have to interchange this with this, this with this, this with this, and at the same time this with this, and so on. Right? So it is not as simple as you thought in the case of shared memory things, right? So in order to do that, let us first consider this example, explain it, and then we will write the algorithm, right? What we do, we copy these things into another array B. Suppose this is the bottom part is A, and we are copy it into another array B. And we have one thing is that diagonal elements are already transposed. You don't have to touch it. Right? Now we define the two operations. One is rotate up. Another one is rotate left. Now in order to define these two operations, rotate up, say we use RU and RL. In order to define these two operations, what we did, we assumed that mesh connected computer wrap around. Wrap around means this is connected and this is connected. Right? You remember the wrap around. Right? So once I tell rotate up, so this up means this element will come here. So if I perform rotate up A and rotate left B, what I get? Five, 9, 13, 1, 2, 3, 4, 1, 6, 7, 8, 5, 10, 11, 12, 9, 14, 15, 16, 13, 6, 7, 8, 6, 7, 8, 10, 14, 10, 14, 2, 7 has gone up, 11, 15, 3, 4, 16, 12. Right? Now you look at the diagonal elements. See, if you see the diagonal elements are transposable. Actually, 2 has to be, original matrix it was 2 and 5, that has to be transposed, agreed? Then 7 with 10, this 2 has to be transposed, and 12 and 15 to be transposed, right? So if you see the diagonal element, these elements are transposable. However, you observe it that this is not transposable. So, after doing this operation, if you find that I is less than the number of elements, then it should be here, I less than n, if then I is interchanged with BII. So, if it is the case, then you get here 5, you get here 2, you get 3, you get 6, 4, 7, 1, 8, 5, 12, 8, 11, 10, 7, 6, 9, 10, 13, 14, 1, 15, 2, 11, 14, 15, 12, 9, 16, 13, 4, 16, 3. So after the first iteration, the data will be like this. Agree? Now you perform again, rotate up A, rotate left B, what you get? Six, 10, 14, 6, 10, 14, 5, 10, 11, 15, 3, 8, 15, rotate up is A. A is 9, 13, 1, 2, 7, 14, 2, 6, 11, 12, 3, 7, 12, 16, 12, 16, 4, 8, and this side is 3, 4, 1, 5, 10, 8, 5, 6, 11, 15, 9, 10, 15, 16, 13, 14. Now after rotate up and rotate left, you observe that these two are transposable elements. You see the original one, that 3 and 9 to be transposed and 8 with 14, right? So these two if you transpose, so here your condition will be if I is less than n minus 1, then AII is transposed with EII. Agree? So what you get here? Nine, 3, 14, 8. And rest will be same. Is it okay? So again you do the rotate up A, rotate left B, so 3 will be here, two will be here, 1 will be here, 13 will come here, 8 will come here, 8 will come here, and 2 here, 6 here, and 7 is here. This side is 12, 3, 7, 11, 16, 4, 8, 12. This side it is 4, 4, 1, 5, 9, 14, 14, 5, 6, 10, 15, 9, 10, 11, 16, 13, 14, 15. Now you observe that these to be interchanged, right? 4 with 13, which is lying here. So next one is that if I is less than 2, then AII is interchanged with BII. So you get here 13, 4, 1, 8, 5, 12, 9, 16, 14, 1, 5, 2, 6, 3, 10, 4, 15, 2, 9, 6, 10, 7, 11, 8, 15, 12, 14, 11, 13, 7, 16, 3. Now you observe that we are almost we have done the transposition work. Only thing is that there is still remaining rotate up and rotate left one, and then little manipulation. Let us see what happens. You have rotate up A, rotate left B, one, 2, 3, 4, 2, 6, 7, 8, 3, 3, 7, 11, 3, 7, 11, 12, 3, 7, 11, 12, 4, 8, 12, 16, 4, 8, 12, 16, 1, 5, 9, 13, 5, 6, 10, 14, 9, 10, 11, 15, 13, 14, 15, 16. Right? Now if I original matrix, it should have been 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Now this is your A matrix, this is your A, this is your B. Now look at A. So 1, 2, 3, 4 you are getting. And then 6, 7, 8 also you got, you did not get 5. Then you got 9, 10, 11, 12. Here you see 11, 12 you got it. You did not get this one and this one. Then 13, 14, 15, 16, you did not get this one, this one, this one, but you got this one. Right? Yes. And this can be done easily if I is less than j, I is less than j, aij is interchanged with bij. Just you interchange 2 with 5, so 5 will come here, 9 will come here, 13 will come here, 14 will come here, 15 will come here, and so on.
So 4 and 13 are also interchangeable, that is, in the
4
first
and?
iteration. In the first iteration, we did only 3 changes in the diagonal. The fourth diagonal is also, means fourth element is also, we can change that.
4 and
13.
4,
The 2 corners.
yeah, 4 and
In the
13.
next iteration also, the both, whatever is there in the diagonal, we would have changed. And then I think we would have got this transpose directly.
So you did not need not to do this?
Yes, sir. Because if we do that 9 and 3 change there and 14 and 8 also, then because we actually what we did is every time we did one less.
Yes.
That's why we got that.
No, but here how many? Here 1, 6, right? 6. So you are avoiding 6 interchanges?
Yes, sir. First it is 1, second it is 2, and the third it is we are avoiding 3.
Yes, yes. Let us see. This is 13 and 14 you want to interchange here?
13 and
So in in that case 4 will be coming here, 13 will be coming here. See, 9 and 3 also will be interchangeable. Yes. So, yes, then in that case that can be done. Yes. Please check that one. If it is the case, then the problem is much simple. Then you don't have to do this one. So for I equals to 1 to n, for j is equals to 1 to n, because you are making busy all the processor, right, for rotate up and rotate left. So I can write do in parallel. So each processor does what? Rotate up A, but before that copy to B is also required. Eij copies Aij to Bij. Right. So this is first job. Second job is for I equals to 1 to n, do int parallel for j is equals to 1 to n, do int parallel. You are doing rotate up A, rotate up B. See, rotate up A means Pij sends the data Pi minus 1j in wraparound, and similar rotate left is Pij sends Bij to Bij minus 1. Now next you will be writing if I is less than equals to n, or let us write here k, and here somewhere I write k equals to n. Then interchange Pii interchanges Pii interchanges Aii with Bii, and then k has to be reduced by 1. Oh, you don't need to reduce k in that case. If vector is whatever is suggesting, then you don't need to reduce the n minus 1, n minus 2. This is you want, it should be what you are feeling, that it should be always this, right? So if it is the case, you don't have to reduce k. Please check it, because I long back I did. So Pii interchanges Aii with Bii, and so you get the things. Then the complexity of this algorithm is constant amount of time using n square processor. So cost is order n square, which is optimal, because in any transpose of a matrix you need n square time. Now what happens to other models? Suppose you have a perfect shuffle computer and you have n square processors. P0, P1, P2 to the power, say 2q minus 1. Right? The processors, we assume in the perfect shuffle that is a power of 2 number of processors, And you remember that it has the three connections, one is exchange, another one is shuffle connection, unshuffle connection. And you have n square elements. This n square element, each processor contains one element. Now, can you give me a little idea how can I? You remember one thing, that any perfect shuffle algorithms is based on the two properties, right? Those properties have discussed. Now, can you suggest how EIJ is stored in P, then A11 is stored in A11 is stored in P0. A12 is stored in P1. A13 is stored in P2. AIJ is stored in I minus 1 right? Right? Because it's an n square processor, so this is n square, 2 to the power 2q is n square, so 2 to the power q is n. Yes. Now, AIJ is stored in this. AIJ has to be moved to the location of this. Agreed? That means the processor index will be this. So the processor Pi minus 1 to the power q plus j minus 1 contains AIJ. He has to send the data to the processor 2 to the power q j minus 1 plus I minus 1. Yes, no, yes, no.
Yes.
Correct. And this can be done by this can be done by Q shuffles or Q unshuffles. Either left shift or right shift Q times. If you do, it will move to that. Yes or no? Rotate Q times. So this will come here, I minus 1 will go there. No. Suppose you have this index, right? So rotate 2 times, you will be getting right. So if you rotate Q times, so this term will come here and this term will go there. So you need the Q shuffles to move the element Eij to its respective area. So you need basically log n time to move the data using n square processor, and the cost becomes n square log n time. Now this is all about transpose of a matrix. I don't think that 3 models will be useful or suitable for matrix transposition, right? So I am not discussing those things. Matrix multiplication. So let us discuss about first sequential algorithm. It is very simple. For I equals to 1 to n, 1 to I equals to 1 to, say you have A equals to C is equals to, generally we write A star B, what is Aij star Bjk, and I is 1 to m, j is equals to 1 to n, and k equals to, say, 1 to f. Right? For I equals to 1 to m, for k equals to 1 to L, Cik equals to 0, for j is equals to 1 to n, Cik plus A j star Bjk. This is the simple sequential algorithm, which is the classical. I am not talking about the Stresson's algorithms or other things. This is simple sequential algorithms. And if I have the shared memory model with the n square processor, I can easily write this algorithm on shared memory. Right? Just simple, I write do in parallel. Do in parallel. And rest is put in your loop. So you have order n time complexity using n square processor, for this matrix multiplication problem. So cost become order n cube, and the classical algorithm also had order n cube. This n square is, with the assumption is that m and l is also order n. Now, today we will discuss only one algorithm, and then tomorrow on mesh connected. Tomorrow, not for next class, because I have to hear from them the term paper programs. Think about, see, till now we have not considered that input-output steps in parallel machines. We assume the data is readily available in the process. As I told you that input-output will play a major role in parallel algorithms, because I/O time sometimes you find that much more than the execution time, right? But here in this, the algorithm, whatever I will discuss, this is based on that input-output and little amount of pipelining and other things will be coming into the picture. Say you have the mesh connected. It is not wrapped. It is not wrapped around it. See, one thing you observe that two elements of two matrices are multipliable if first one's column index is matching with the second one's row index. So that is the thing you have to keep it in mind. Okay, let me connect this one, otherwise you may not get. So on. See, the data is arranged in this form, right? A11, A12, A1, N is nearer to this, and then one delay is here, A2 delay, and so on. Similarly is the case with matrix B. Now, you move this data after one cycle and this data, and you observe that they are multipliable. So once you moving this one, this data is moved to this place, this data has been moved to this place. So next cycle, this data will be here and this data will be here, which is multipliable and which is to be stored in C11. And at that time, this data will be moved here and this data will be multiplied, and which is also multipliable, and so on. So after, if it is, actually I have taken n, okay. So after you will find n plus n minus 2, that many operations, all the data will be multipliable and stored in the appropriate place. Because this data has to be moved here, this data has to be moved here. The distance will be m plus k plus n minus 2. Right? Because this delay is there, the delay will be factored m minus 1, and that's side k minus 1, and n movement, so it is m plus k plus n minus 2. Okay? So you have n square processor, and Pij receives at any instant of time one data from this side, another data from this side, multiplies it, stores it in Cij or adds with Cij, then Pij sends this data to Pi plus 1j and sends this data to Pi minus 1j, and so on, it iterates. Agree? So after n plus k plus n minus 2 iterations, the matrix multiplication will be ready. So basically, it is order n time using n square processor, which takes order n cube time cost to multiply the two matrices. We'll discuss in the next class what happens if the elements are stored in the matrix. Now, it needs little additional manipulation. If you see that if you put Eij and Bij, both are in the ith row and jth column of the processor, Pij contains Eij and Bij, they are not multipliable. Right? Pij and contains Eij and Bij, they are not multipliable. You have to get Pi, such the situation is like that Pij contains Eij and Bji. Then only multiplication is permissible, or Bjk. So you need to do little operations on that. So we'll discuss that one because that will take little time to explain. So
parallel dynamic programming, like with respect to a sub-problem of sequence alignment.
tell me a problem.
Yeah, sequence alignment. Sequence alignment, like the basic problem is you got two sequences of M and N, say DNA sequences, and you need to align them. You need to reduce the, like I should introduce the problem and stuff. Okay.
Because others may not know your
Okay.
because there is another boy who is another team working on bioinformatics.
On
Same thing, sequence alignment.
Now you explain. First you explain, then
so like two teams can work on the same
no.
problem. Well, I define a scoring pattern like about the sequence alignment problem.
First you tell the problems, then the others will opine on it.
Okay. Yeah. So I got the scoring pattern like say these are the two sequences A, C, T, G and say G, A, C, T. So I say that in the case of match the score will be +1. In the case of and in the case of mismatch the penalty will be mu, and for a gap I can introduce gaps, and for a gap the penalty will be minus lambda or something, minus sigma.
Not lambda, it is sigma.
Yeah. Yeah.
No, what is gap or another? While you explain the problem, you tell the problem. What is the sequence? ACT is a sequence.
Yeah, I'm coming to that, what a gap is and stuff. Well, like, so this is the first sequence. Now I can put this G either here, or I can put a gap and start the second sequence from here and stuff like that. So, or I can also put start the second sequence here, meaning I put a gap here, and I'll match the second point of the second sequence with the first one of the first sequence and stuff like that. So if I put it like this, so there will be a gap here obviously. So here I'll be having a penalty of 2 sigma, and there are 3 matches, so it will be +3. So the score for this particular alignment is this. So what I need to do is I need to maximize the scoring.
No, then it is minus 2 sigma.
Yeah, sorry, yeah. Minus 2 sigma +3. So I need to maximize the total score possible. So this is the basic problem of sequence alignment. And the deep dynamic programming approach to this problem, like say if I got 2 sequences of n and n, so it takes order n square. So that will be nothing but like this is the standard way of doing that. So I construct the matrix of n by n. So this is the first sequence, and this is the second sequence, and every alignment will get a path from here to here, from this point to this point. And for example, this particular alignment, like say it'll be like I start from here and I've got a space here, so that means I'm moving on the second sequence, but I'm not moving on the first sequence. So it will be something like this. So I come down, and then there is a match between A and A. So I'm moving on both the sequences. So it's like this, and I'm moving simultaneously on both and both. And finally I'm moving on the first sequence, but not on the second sequence. So this path defines this particular alignment. So I got, for every such alignment, I'll have some path from here to here. So what I need to do is I just need to maximize the scoring on this path. So in the dynamic programming approach, what I can do is I can for every such position, I can So say I got a position here. So I can come into this position either from this place, or from this place, or from this place. So there are only 3 ways of entering the position, and if I know all the smaller problems, all the best ways till, if I know the best way till here, and till here, I can easily compute the best way till here. So in meaning that I got the overlapping subproblem structure and also the optimal substructure. So the dynamic programming approach is applicable here, and I can do it in order n square time. Like by sort of like anti-diagonal sort of way. Like I can compute all these things together, and I can do all these things together, because these will depend only on the things which are lying on this side. Similarly on these. and stuff like that. So the normal sequential algorithm will take order n square time, and what we need to plan is we need to we plan to look at all the different possible parallel algorithms that are there for DP problems, and propose a better better algorithm is possible. Well, the most basic, the parallel algorithm can be like if you have got order n processes, shared memory model. So you can reduce the time to order n. You can reduce the time to order in a straightforward fashion, because all the diagonals you can do them in a parallel way. You can also use the row by row approach. That is, like, I start from here and I compute the best path till these points. First I compute this, then this, and this, and then this.
No, but this problem, who is doing?
Yes. So it's the same problem.
So now one of you, they have already reported that this type of problem.
We can take some other problems in the
sequence alignment.
Sequence alignment.
Like there are some
open problems are there. 4, 5 open problems.
But it should be feasible also, right?
Yeah.
Solve open problem and you are solving.
Hey, it's not exactly open problem like
It's
in
closed problem.
the traditional way. When you mean an open problem, it's like no one has been able to solve it. It's not. I don't think they're so hard.
What is the problem?
The one problem is you are given two sequences U and V, and that is given that the ith character of one sequence and jth character of the second sequence, they are basically matched, and you have to, and in that case you have to find the best alignment.
You're fixing.
Go ahead.
Like you've got two sequences. Say I fix this. These two have to be aligned. So now get the best alignment for the two sequences. And also you can also try the circular alignment. You've got two strings, and like exactly it's like, so I can cut them anywhere, like sort of. So you've got two such circular strings. So what I want to do is I want to align them.
See, I can tell you one problem. You can try that one.
Yes.
A sequence is known as k-sorted. K-sorted means that an element, ith element, should be in the ith position. That is, the ith shortest element should be in the ith position. Instead of ith position, it may be at a distance of I.
Like I position or less than I position.
Or greater than also.
Okay.
So you, right?
What do you mean by distance?
Distance, but I should be here instead of here. It is one. It may be in the within the certain range.
Okay.
Say you write down a number, it's a sequence of integers.
Sorted sequence.
Integer sort.
Sorted sequence.
First you write integer sorted sequence. Okay. Say actually, I am not talking about this type of thing. I am talking about you know what is integer sort.
Okay. I don't know.
You don't know? Integer sort is that a permutation of n integers, first n integers.
Okay.
Right? So 1, 2, 3, 5 elements are there. So 1, 2, 3, 4, 5. Write down 1, 2, 3, 4, 5. And another permutations you write of 5 elements.
Or the same 5 elements.
Ah, 5
Yeah.
elements. Right? See, 1, 2, 3, 4, 5 is your sorted sequence. The distance is 0. So 3 has occupied its own position.
Okay.
Right? No, not niche wala, upar wala.
Okay, fine. Everything else upward.
I am talking about the bottom one. So it is that you are telling that it is 3 sorted. Why 3 sorted? That every element are at a distance of plus minus 3.
Plus minus 3, yeah.
Right? So I am telling it is a 3 sorted. When 3, so if k equals to 0, it is a sorted sequence. K equals to 1, that k equals to 1 means it is almost sorted. It is almost sorted. Only one distance may be here or there. You understood? Two sorted means it may be 2 elements away or 2 elements this way. right?
From the actual position.
From the actual position. So can you think about that problem? Then I'll sort it. Why shall I do your thing? Right?
Yeah.
So can we have order n algorithm or some? It must be a function of k. K sorted is a function of k in such a way when k equals to I'll write 0, then it should be a
sorted.
n log n time
Yeah.
sorted sequence. Right?
Yeah.
You think that one. Because this is somebody has done already taken. Or worst case, you take whatever the other one you told that given two sequence, one is fixed.
So my work is basically around the decomposition of a matrix into singular value decomposition. Okay. So I mean this is basically used like in any search engine. Basically there are two things: terms and documents. So like there's a in a search engine there's a matrix which has terms on this side and documents on this side. Okay, so for in every document there is a term and there is it may be the repetition of terms in the document. So this matrix basically contains this document has how many times this term, like document T1 and term T1. So if T1 comes 4 times in this document, so this entry will be 4, and if this term in Ti, if this comes 10 times, this entry will be 10, maybe 0, maybe 0. So for a search engine, these metrics are very large. I mean it may be around 1000 cross 1000, maybe more than this. So basically to store these type of matrices, what is basically done, they have to store it some reduced form structure. Okay, so like this is a matrix, so this is basically converted into its singular value decomposition, like U, this, and V transpose. So U and V are the orthogonal matrix. Orthogonal means U transpose equals to 1. These are the orthogonal matrix, and this sigma basically contains the singular values of this matrix. So so this is stored and after this we'll take the rank of A, like K, this is the K rank, okay, and it is stored as A K is equals to UK sigma K and V T K. This is another form, I mean, to store the rank.
What is AK?
K is
What
rank.
is AK?
AK is rank of K, matrix with rank K. Okay, so basically our main intention is to find this thing. Now this is very dynamic matrix. I mean documents are adding and terms are adding very frequently. So let's say once you find this thing, then again after some time a document added and this number gets changed to 10, this number gets changed to 5. So again we have to find out this thing again. So what I am doing, I am finding basically the parallel algorithm to find this singular value decomposition. So this is basically the problem.
How can a column change?
Sorry,
Even if you add a new document, for document even the terms will be like, you know, so even the document is change, right? You're not adding new documents, you're changing the original document.
Document can be added, but right now I mean I am basically intending to change in terms. So I mean this will change, this will change, this will
What
change.
is telling that can there be possibility to have new terms?
New terms. So this is I have not searched.
No, this is you have T1, T2, T3, TUAN, n terms are there. Can there be another term say Tn plus 1?
Tn plus 1.
Or in a given document, T1, the number of occurrences of T1 can change.
I mean, in
Number
a
of occurrences,
number of occurrence can be changed.
How?
You're modifying the file.
Modifying the file, modifying the document. This is all. So, or I think terms can also be changed. But I didn't search about this whether terms and documents will be changed. I just find out.
No, I am not sure that how you are changing. Documents are getting changed.
I mean, documents are changing very.
Content of the document.
Yeah, I mean these web documents are changed very frequently. So these ranks, the web page ranks are changing very
No,
frequently.
ranks are different, but
I mean,
content of the see.
So another thing, let us say I am only maintaining the top n documents, and a particular document is not being accessed that frequently now. So it moves down the list out of the n, and some other document comes in. So let me say my ith document has moved out of the list. So instead of the ith document, I am having a new document. So that is equivalent to saying that the terms in the document have changed.
Are you planning to, what he is telling, are you planning to keep the information of the terms with reference to the highest degree of frequency?
No, basically, I'm just giving the application. I mean, this thing can be used here. I mean, I'm basically.
No, the matrix size, let me answer you on the matrix size, is it constant or variable?
Matrix size. So, whenever this will be calculated, let's say t equals to 0 pe, this matrix size is some n cross n, and it may be after t times n plus 1 cross n plus 1. So for n plus 1 cross n plus 1, this will again be calculated. So calculation of this thing is.
See, here there are two components, my feeling. One for given a matrix A, n cross n, you are updating the terms and all the content of that Tij or whatever it is.
Yeah.
And you are modifying. That is one thing. Another one is that no, matrix also dynamically.
No, I'm not changing the matrix size. I'm just changing the entries.
Content of the.
Content
but
of
you are
the.
assuming the
Yeah.
matrix is n cross n.
Yeah.
Okay. The problem is then simple.
Yeah.
Because if you change the matrix size, the problem becomes more
Yeah,
complex.
more complex. So this is basically the idea.
In that case, if you are considering matrix size is same, are you arranging this data T1, T2, Tn rows based on the number of based on the frequency number? Highest frequency would be the first row, second highest. Frequently,
No, I'm just just changing the entries and just converting it into some compact form. This is the only thing.
So most referred thing should not be in the first.
Most referred thing should not be
In the first row. Is it the no.
No.
But I don't know. But there is a maybe solution exists.
Solution.
Sequential solution exists, right?
I mean, there are some ways already exist to find this
Sigma.
Singular values of a matrix.
Of course it is there.
Yeah.
So, okay, let us see. Because here the inverse will be coming into the picture. So I don't know. Sharad's just done, right?
Yes, sir. So, sir, like, I have two problems in mind. So, one is like a parallel minimum spanning tree problem. So, like minimum spanning tree algorithms. So,
Several algorithms exist.
Yes, sir. So, like, what I found is that there, like, one particular paper has given two parallel algorithms to find like the bulk synchronous parallel model, like not shared memory model, but they have given two algorithms with their defined time complexity. So what I suggest is like perhaps I'll go through the algorithms, I'll read through them, and like perhaps afterwards should suggest a algorithm in a different model, maybe a shared memory model or.
Shared memory model also exists. Okay.
Yes, sir, in this thing.
Oh, what is the second problem?
So there is like clustering problem, that is like hierarchical clustering.
Victor, you are doing right.
And okay, there is one more problem, single source shortest path problem. So there is like
Pooja is doing, I think. Similar type of thing. Huh? No, you are Sander here.
No, we are doing now parallel data.
Oh, you are doing parallel. So now you tell.
So one more problem is like single source shortest path problem.
Explain.
So actually, like given a problem, like given one particular node in the graph, we tend to find like shortest path to all the nodes in the graph. So there are like the discharge algorithms can be used to finding that, but we tend to find like using the shorter like.
Why you cannot find it? Discharge algorithm can easily be implemented.
Yeah. But like we tend to find some parallel algorithm to do that. They are given like many parallel algorithms for that also, but like we tend to refine on that given algorithm because there is one given algorithm by I guess author called Canas. So he has given like algorithm which does like which has a cost of n to the power 3/2 log 4n, and there is one more algorithm that has been given recently by author that has given a refinement on that. So he tells like he can like there is a variable like epsilon in that complexity. So like we can refine on the value of epsilon it can be reduced to less. So like there is like a possibility in that.
So what are the problems here?
So single minimum span tree and single source problem.
Difficult one. So any comments you want to give to him or any suggestion? Because both the problems, are classical problems, and by now you may get several solutions to these problems. Only thing is that if you change the model, you can think about
Yes,
it that only way. Otherwise, I don't know. You have to work very hard. Otherwise.
So in this particular problem, the minimum span tree problem is thought on like the problem solution that have the paper you found is like given in the bulk synchronous model. So perhaps like suggest a similar algorithm on those lines in the shared memory model.
Okay. But I'm giving you the word of questions actually. That is the thing. You have to work little hard.
So,
right?
or any updates I'll like keep.
Looking good. Okay.